BEC. When a Bose-Einstein condensate, we have a Bose gas, an ideal gas, where some finite fraction of all the particles are in the ground orbital. So if we wrote the total particle number, capital N, as the integral over energy of some particle density per unit of energy n sub e, if we by convention say the ground state orbital is at zero energy, in a BEC the particle density per unit energy has a delta function spike at the ground state orbital, and then a distribution smoothly varying for all the excited orbitals. And we call it a BEC if, as we consider the system size getting large, the number n0 of particles in the ground orbital divided by the total number remains positive as n gets large. So since we're going to have, for a very large system, a huge number of particles in the ground orbital, we will take the chemical potential to be essentially zero, to go to zero in the limit of large n. So in the case when we're in a Bose-Einstein condensate and n is very large, we can consider mu to be zero, and the activity e to the mu over t to be essentially 1. In general, the Bose-Einstein distribution giving the expected number of particles in an orbital with energy E can be written as 1 over lambda inverse e to the epsilon divided by tau minus 1, where lambda is the activity. But we'll be considering the case when we're in a Bose-Einstein condensate when we can take the activity to be 1. And so the total number of particles in excited states as a function of the temperature can be found by integrating over energy the density of orbitals per unit energy, d of e, times the distribution function, which, setting lambda equal to 1, we can take to be 1 over e to the mu over tau minus 1. Well, if we consider, these are bosons, so they have integer spin, and if we consider the case where they're spinless, or spin zero, there's no spin degeneracy, then the density of orbitals as a function of energy we saw can be written as the total volume divided by 4 pi squared. This is for spinless bosons in 3 dimensions, 2m over h bar squared to the 3 halves times energy to the 1 half. And so, rewriting the integral as an integral over a dimensionless variable, defining x to be the ratio of energy to temperature, I can convert the energy over e, dE over e to the 1 half, to an integral dx, but then I have to multiply by a factor of temperature to the 3 halves. So I have a prefactor coming out of the integral from the density of states, v over 4 pi squared, 2m over h bar squared, to the 3 halves, the factor of tau to the 3 halves, which I just mentioned, and then the dimensionless integral dx, which is being integrated from 0, the energy of the ground orbital, up to infinity, x to the 1 half, coming from the energy to the 1 half and the density of orbitals, divided by e to the x minus 1 coming from the Bose-Einstein distribution function. So this is just some dimensionless number when we do the integral, which we'll choose to write as another dimensionless number times the square root of pi. And then remembering that the quantum concentration, which we defined earlier as mass times temperature divided by 2 pi h bar squared to the 3/2, we can write our expression for the number of particles in excited orbitals, and we can divide by the velocity to get the concentration. The number of particles in excited orbitals divided by the volume is just a number, 2.61, times the quantum concentration. And that formula is correct as long as the activity is essentially 1, which will be the case if a finite fraction of all the particles are in the ground orbital. Or in other words, if the concentration of particles in excited orbitals divided by the total concentration is less than 1. 1 minus this quantity will then be the number of particles per unit volume in the ground orbital, which in the limit of large volume will be a very large number, so the activity can be set equal to 1. In fact, then, we can write the concentration of particles in excited orbitals divided by the total concentration when it's less than 1 as the temperature divided by some special critical temperature called the Einstein temperature to the 3/2 power. Since the quantum concentration scales like temperature to the 3/2, so does the concentration of particles in excited orbitals. And when tau reaches tau Einstein, it goes to 1, and then at still higher temperatures, the concentration of particles in excited orbitals is, or divided by the total concentration, is 1. We're no longer in a Bose-Einstein condensate. The activity moves away from 1, and our formula no longer applies. But we can write this formula when tau is less than or equal to tau Einstein. And tau Einstein, 1 over tau Einstein to the 3/2, is just the coefficient in this expression when we divide it by the total concentration of tau to the 3/2, and can therefore be written as 2 pi h bar squared divided by m, concentration divided by that number 2.61 to the 2/3 power. Well, we can give an interpretation of the Einstein temperature, which we had encountered earlier in talking about how to think about the quantum concentration. At the Einstein temperature, there's some corresponding thermal de Broglie wavelength, which I can get by setting the Einstein temperature equal to h bar squared k squared. I'll call it k Einstein divided by 2m. So that's the wave number, the thermal wave number at temperature equal to the Einstein temperature. So we can see from this formula that k Einstein squared is 4 pi n over 2.61 to the 2/3. And the concentration goes like 1 over the typical interparticle spacing. cubed if we're in 3 dimensions. So A equals inner particle spacing. So this goes like 1 over a squared. So in other words, the thermal wavelength at the Einstein temperature, call it lambda Einstein, is of order the inner particle spacing. So if we are starting at a temperature above the Einstein temperature, the thermal wavelength is short compared to the inner particle spacing. The inner particle spacing is determined by the density. So suppose we have a fixed volume and a fixed number of particles, so the total number of particles per volume is fixed. And as we reduce the temperature, the thermal wavelength gets longer and longer. Eventually it becomes comparable to the distance between particles, and that's when the Bose-Einstein condensate forms, and some finite fraction of all the particles enter the ground orbital. Okay? So onset of BEC, as we cool with N fixed, occurs when a thermal wavelength is comparable to interparticle spacing. So we're very far from the classical situation where we can think of the particles as being point-like classical objects. Their wave nature, their de Broglie wavelengths are important in that regime. So this temperature to the 3/2 power means that if I consider the density of particles in excited orbitals as a function of temperature, it turns on like tau to the 3/2, and that means that since the let's suppose I normalize by dividing by the total concentration, so it goes to 1 at the Einstein temperature. At 0 temperature, all the particles are in the ground orbital. And that fraction goes to 0 at the Einstein temperature. Below the Einstein temperature, we can take the activity, we can take the chemical potential to be essentially 0, the activity essentially 1, and then when the temperature gets above the Einstein temperature, the chemical potential backs away from 0, takes negative values. And from then on, the fraction of particles in excited orbitals is stuck at 1, and the fraction in the ground orbital is 0. So what is this Einstein temperature in practice? Is it some ridiculously small temperature that we'd never care about in the laboratory? Well, suppose we consider an atom which is a boson. What's the lightest atom you can think of which is a boson? Well, that's a good one. Well, let's stick with that one. Okay. Helium-4. How do you know that's a boson? Well, what's its atomic number? Well, that's its atomic mass. What's its atomic number? Right. So if its atomic number is 2 and it's neutral helium, how many electrons does it have? Okay. And there are protons and neutrons in the nucleus. How many of those are there altogether? 4. So the electron is a fermion. The fermion, the boson, sorry, the neutron is a fermion. The proton is a fermion. They all have spin 1/2, right? But when you put together altogether 6 fermions, you have a boson, right? An even number of fermions makes a boson. you have an even number of fermions, you exchange even number of fermions here, even number of fermions here, then the total number of minus signs is an even number, so there's no change in the sign of the wave function when you do an exchange. Whereas if you had an odd number of fermions, then you'll have a minus sign when you do the exchange. So an odd number of fermions means a fermion. So this is a boson. And I picked that one because it's pretty light, and the Einstein temperature goes like 1 over the mass. If I put in the mass of a helium atom, and I can look up the concentration of helium at low temperature and atmospheric pressure, which is 27.6. 27.6 is the reciprocal of the concentration in centimeters cubed per mole. So I can put that in, and the mass, which is essentially 4 times the proton mass, 6.6 times 10 to the minus 24 grams, and I get a temperature. I get an energy. With Boltzmann's constant, I can obtain the corresponding temperature, and that turns out to be about 3 degrees. Okay. That's at 1 atmosphere pressure, where I have that value of the concentration. Well, helium is interesting because even at strictly 0 temperature, at atmospheric pressure, it does not solidify. It does not form a crystal. Most materials do form a crystal at sufficiently low temperature. They solidify. Helium does too at sufficiently high pressure, at 25 atmospheres and above. It forms a crystal. But helium at laboratory pressure is actually a liquid even at 0 temperature. Normally you think of a crystal melting because of thermal excitations of the atoms in the crystal. They vibrate more and more as you heat it up. Eventually it liquefies. In helium, the atoms are light, and their interactions are quite weak, so that just the 0-point motion of the helium at 0 temperature is enough to keep it in liquid form, prevent it from solidifying. So helium-4 is a liquid, not a crystal. At 0 degrees and 1 atmosphere pressure. So, does something interesting happen at about 3 degrees Kelvin? No, nothing interesting happens at 3 degrees Kelvin. But something interesting does happen at a slightly lower temperature. The phase diagram of helium-4 looks something like this. This is 25 atmospheres. Pressure, we get solid helium when the pressure is high enough at low temperature. Then there's a liquid phase, even at very low temperature. But actually there are 2 liquid phases, and they're separated by a phase boundary. This liquid phase is called helium-1, and it's the one that occurs at sufficiently high temperature. But then when you cool the helium down, it turns into another form of matter at a certain critical temperature. It's not 3 degrees, but it's not so far off. It's 2.17 degrees K. Why isn't it exactly 3 degrees? Well, because in helium, the interactions can't be completely neglected. There are interactions. And one has to do a rather sophisticated calculation to understand why this is the temperature at which a phase transition occurs. And it's been done. It's a large-scale numerical computation, computer simulation, and you have to put in the known properties of the interactions among helium atoms to do the calculation, but it works. You can get 2.17. Yeah.
Below 2.17 Kelvin, is there like a little bit of helium-1 still left, or is it only 2?
Well, in a sense there is. I mean, helium-2 is the name that we give to helium in its superfluid phase. What happens below 2.17 degrees is that helium can flow without any viscosity, without any resistance. That's why we call it a superfluid. Viscosity, essentially. We'll talk a little more about viscosity in the last week of the class, but it essentially means resistance to flow. And the interpretation, it's a little bit loose because the interactions can't be completely neglected, is that at this temperature, a Bose-Einstein condensate of helium atoms forms. And so we can really think of the system as consisting of two fluids, which is a way of answering your question. This is actually the same picture I drew earlier of the number of particles per unit energy has a big spike if it were an ideal gas of atoms in the ground state, and then a smooth distribution of excited atoms. The atoms which are in the ground state really are the Bose-Einstein condensate atoms, and they have no resistance to flow. That's a superfluid. And these excited guys behave like a normal fluid. Which does have viscosity. Okay? So these two fluids kind of coexist. But if I, say, have a container of helium-2 and cut a tiny little hole in it, stuff comes flowing out, which is essentially the superfluid component of the liquid helium. The normal fluid, because of its viscosity, can't squeeze through the hole, but the superfluid can. Now, the theory we developed, which is really the theory of an ideal gas, doesn't fully explain the superfluidity of liquid helium because the interactions really are important. And I'll try to give you an idea of why that's the case in a minute. But we can ask the question, if this has something to do with Bose-Einstein condensation, what would be a good way to check that? What's a lot like helium-4, but different?
Helium-3?
Yeah, there's another isotope of helium. And is that a boson or a fermion? How many electrons? How many nucleons in the nucleus? So how many fermions total in a neutral helium atom? So is it a boson or a fermion? It's a fermion, right? Unlike helium-4. Chemically, it's very much like helium-4. So what do you think would happen if I liquefied helium-3 and cooled it down to 2 degrees? Nothing. Right, nothing happened. And then you keep cooling it, to 100 milligrews, nothing happens. 10 milligrews, nothing happens. Question?
So helium-2 is the superfluid, right?
Is helium-3 a superfluid? Is that?
No, I'm saying
Helium-4 is a superfluid, right?
Yeah, but which type?
Oh. Which type?
Yeah. Okay.
Well, what I meant, you mean, but what did I...
It means which liquid phase. It means liquid helium-2. On the diagram above.
Right.
Phase diagram.
Right, this is the superfluid, I see. Right. So we would like to interpret that phase of helium at sufficiently low temperature as being a condensate in which there are many helium atoms in the ground orbital. And here, the fraction of helium atoms in the ground orbital goes to 0 for a large system. So helium-1 has viscosity. When helium-2 forms, it's a very noticeable change. Now it flows without any resistance. It has very high heat conductivity. It's really a very different beast. And there's a phase boundary separating the two types of helium. Anyway, what happens with helium-3 is pretty interesting. You cool it down to about a millidegree, and then a superfluid forms. Right? Not 2 degrees, but a smaller temperature by about a factor of 1,000. What do you suppose is happening there? Well, what we think happens with helium-3 at sufficiently low temperature is that helium atoms form bound pairs. 2 helium-3 atoms form a kind of molecule, and it's a complicated story, what gives rise to the attractive force that makes this molecule. But it's a very weak force, so the molecules break apart because of thermal excitations at a very low temperature, like a millidegree. But at sufficiently low temperature, these pairs of helium-3 atoms, which are bosons, can condense. They form a Bose-Einstein condensate. But we only see it at very low temperature because the pairs get broken by thermal effects for a temperature above a millidegree. Okay, so I said I'd explain a little bit more why interactions are important for understanding superfluidity. What kinds of interactions are there? Well, actually, you can understand superfluidity with a model in which the interactions are just hardcore interactions, no long-range interactions between helium atoms. But when you try to bump them into one another, there's a hard core. Now, it doesn't cost you any energy for them to get any closer until they touch. And then you can't push them together any closer than that. That's what I mean by a hard core. So what's really the key for making superfluidity work? Why should there be flow of a liquid without any resistance to flow, without any viscosity? Well, you can think about viscosity in the following way. If I drop a marble into the liquid and it starts to fall, does the fluid resist the fall of the marble? Okay? If it does, then there's some kind of damping force on the motion of that object. And let's just think about the kinematics of that. I've got some big object. We can imagine it's a sphere, but it doesn't really matter. But it has a large mass compared to the masses of the individual helium atoms. And it's moving along with velocity v. And what would cause it to lose energy? Collisions with the atoms. So there could be a process in which an atom collides with this big object, or an atom gets excited by the motion of the large object. So it recoils slightly. It has a modified velocity, and in the process, an atom gets excited with energy E and momentum P. Okay? So there's dissipation of projectile motion because of collisions with atoms. So let's do the freshman physics of understanding this collision. There's conservation of kinetic energy. We have an atom which I'll imagine is initially at rest, gets excited by the motion of the projectile. The projectile's velocity changes a little bit. Since kinetic energy is conserved, the initial kinetic energy of the projectile is equal to its final kinetic energy plus the energy acquired by the atom. And we also have momentum conservation. So that the initial momentum of the projectile is equal to its final momentum plus the momentum of the atom. So if I subtract p from both sides and square this equation, the conclusion is that m squared v prime squared equals m squared v squared plus p squared minus 2m v dot p. V the velocity of the projectile, p the momentum of the atom. And if I also multiply both sides of the... Oh, what happened? Why don't you guys stop me when I do things like this? So if I multiply both sides of that equation by 2m, and then isolate m squared v prime squared on one side, m squared v prime squared is equal to m squared v squared minus 2me. Okay? So since these two things are equal, the m v squareds cancel, and so the energy acquired by the atom in the collision I can write as v dot p minus p squared over 2m if I divide both sides by 2m. And actually this mass is very large. We can imagine it's much larger than other relevant parameters, so I can ignore this term. So if there's a kinematically allowed collision which allows the projectile to lose energy by exciting an atom, the energy of the atom, which has momentum p, will be equal to the velocity of the projectile dotted with the momentum of the atom. So that means the collision will not be kinematically allowed, and therefore there will be no dissipation. If the energy of atom with momentum p is greater than pv, the dot product can't be larger than the product of the speed of the projectile and the momentum of the atom. So that means we can identify a critical velocity that if the projectile is moving slowly enough, there will be no resistance to flow. The critical velocity will be the minimum value of energy of, well, whatever elementary excitation is being excited by collisions with the projectile, the energy of that excitation divided by its momentum. So if V is less than V critical, then I'll call them elementary excitations. Cannot be excited. So no dissipation. Well, if the elementary excitations were non-interacting atoms, if we really had an ideal gas, the critical velocity would be the minimum of EP over P, but EP would just be P squared over 2m. So that would be P over 2m. And its minimum occurs when the momentum goes to 0. So we would conclude that the critical velocity is 0. And that would mean no superfluidity. There would be dissipation at arbitrarily low velocity. But that's not what happens in helium. And to understand why it's not what happens, you have to look more closely at the effects of the interactions among the atoms. So there are really two things that are crucial. One is some kind of repulsive interaction at short distances, what I call the hard core. But the other is, we have to remember that they are bosons. And so the wave function has to have the property of being symmetric under all possible permutations of the helium atoms. So to get a more sophisticated theory, we have to include two things: short-range repulsive interactions among the atoms, and secondly, well, Bose statistics, i.e., the many particle wave function is completely symmetric under permutations of the particles. I can exchange any two particles and the wave function stays the same. So I can build any permutation of the particles out of a sequence of transpositions. So for any permutation, the wave function has to be unaffected. And so it isn't quite right to think of the elementary excitations as being excitations of a single helium atom, because we have to take into account that they're all indistinguishable. They're really collective excitations of the fluid. And what really happened was first suggested by Landau, worked out by Feynman in more detail, and nowadays it can be done with these computer simulations with great accuracy. If one looks at the energy of the elementary excitations as a function of their momentum, at low momentum the excitations are phonons. They're sound waves in the helium. And they have a linear dispersion relation with energy going like momentum. The phonons have energy equals momentum times speed of sound. And then some kind of complicated stuff happens which you need to take into account the hardcore interactions to understand. And the dispersion looks something like that. And so what determines the critical velocity is really this tangent to the curve, which has the minimal slope. And that's the critical velocity. And the excitations in this little dip in the dispersion relation are called rotons. And they're called rotons because you can think of them as being excitations in which locally the fluid is rotating. But you have to quantize that rotation to get the dispersion relation in detail. So if the velocity is below the critical velocity, you just can't excite anything, and there's no resistance to flow, and that's why it's a superfluid. But just treating it as an ideal gas isn't enough for understanding what's going on. Okay. So what I'd like to talk about next is not described in the book because the book is too old, but there are notes on the website about it. And that is Bose-Einstein condensation in dilute atomic gases. And because, well, we're now going to consider gases which have a low concentration, very dilute, compared to liquid helium, the ideal gas approximation, although still not exact, and it's important that it's not a perfect ideal gas, as we'll see, is a much better approximation. So our theory of Bose-Einstein condensation is more reliable in the regime of dilute atomic gases. It wasn't until 1995 that Bose-Einstein condensation in an atomic gas was achieved for the first time. And the book was updated in the 1980s, and that's why it's not discussed. The first two atomic BECs were achieved in alkali metals, rubidium-87 and sodium-23. Well, you know these are both alkali metals. Anybody know the atomic number of sodium? Okay. Well, how about rubidium? Think about the periodic table. Let's see. There's an inert gas over here at 36, and then it's 37. So, of course, they're odd numbers, and that means that we want an odd atomic mass in order to have overall a boson, right? We have an odd number of electrons, an odd number of nucleons in the nucleus, and then we have a boson. And what's nice about these guys is they're easy to control with lasers, so it's really for technical reasons that sodium and rubidium were the easiest. And that was first done in 1995, as I said. And then it led 6 years later to a Nobel Prize for the guys who did it. Rubidium, it was Cornell and Wyman. And sodium, Ketterle. And partly for fun and partly for academic rigor, on the website I put links to a website that Cornell and Wyman designed to explain how Bose-Einstein condensation was first achieved, and an article written by Ketterle a couple of years after his first experiments explaining what he did. Now, what do I mean by dilute? I'm talking about a very cold atomic gas with a density of about 10 to the 14 atoms per cubic centimeter. Okay, so much more dilute than liquid helium. And so for the atomic masses appropriate for rubidium or sodium, we can estimate the Einstein temperature. And when you do that exercise, you find a number of about a microdegree Kelvin. Okay, it's much less dense, and therefore the Einstein temperature is much lower. Okay, about 10 to the minus 6 K. So that's going to be hard, right? We have to cool to a microdegree. But it's been done, and people had to work hard for years to figure out how to do it, and they're proud of that achievement. So they call this temperature regime ultra cold. So we're talking about dilute and ultra cold atomic gases. Okay, so how do you do it? So first of all, you got to trap the atoms. Okay, how do you do that? Well, you can do that magnetically because the atoms have magnetic moments. What you need is an inhomogeneous magnetic field, which you remember will then apply a force to a magnetic moment. If you can polarize the atoms, their magnetic moments are aligned in a known direction. So you can apply a force with an inhomogeneous field, which will keep them confined inside the trap. Okay, but we got to make them cold, and that's done in 2 steps. So the first step is called optical molasses. That's not how you spell molasses, though, not even close. I think it's probably 1 L and 2 S's, but I don't know how to spell molasses. What you do is you got these trapped atoms. Here they are. And then we shine lasers on them from different directions. The 3-dimensional trap, and we shine lasers from each of 6 directions, say. And the frequency of the laser light is chosen in the following way. The atom has some transition from its ground state to some excited state. And the energy associated with that transition is h bar times some characteristic frequency of the atom. And then we choose the frequency of the laser light, its circular frequency, to be slightly less than that. Okay? So that means in order to be excited by the light, the atom has to be moving towards the laser. If it's moving towards the laser, it sees the light slightly blue shifted. It gets shifted up to a sufficiently high frequency for the atom to absorb the light, getting excited from the ground state to this excited state. Okay? Once excited, the atom can then emit a photon spontaneously and decay back down to the ground state. But when it decays, the photon it emits is emitted isotropically, as likely to be emitted forward as backward. So the excited atom emits a photon in some direction, and then it recoils. So because it's absorbing light coming from a preferred direction, a preferred laser which is blue shifted correctly, the one that it's facing rather than the one behind it, but it emits the photon isotropically, it's more likely to slow down than to speed up. So it cools a little bit. And after many such collisions, the atoms are cooler than they were initially. That's optical molasses. And with optical molasses, you can cool an atomic gas down to, maybe about 100 microkelvin. Now that's getting pretty cold, but not nearly cold enough. And on the website that Cornell and Lyman design, you can play the optical molasses game and get the frequency right so the blue shift cools down the atoms. But it's not enough, so you have to do something else. What else can you do? Anybody have any coffee this morning? None of you had coffee? Okay, thank you. So you poured yourself a cup of coffee, and you sipped it a couple of times, and then you noticed that what was happening to it. It's getting cool. And, the main reason it was getting cool was you probably saw steam rising out of your cup.
I didn't really let it sit that long. I drank it pretty fast.
Oh, you did? All right. Well, all right. But I also had coffee, and I had to reheat it in the microwave because I didn't drink it fast enough. That was dominated by evaporative cooling. So in my coffee cup, the hotter molecules were escaping through the top of the cup, carrying away some heat and cooling the remaining molecules. That's evaporative cooling. Well, we can use that in our atomic trap. We have a trap. At the bottom it's roughly harmonic, but then it has edges that are rounded off. There's a top of the trap. This is supposed to be now a potential energy diagram illustrating how the potential energy of the trap depends on position. This is the height of the trap in energy, but I can slowly lower it. And then some of the hottest atoms will escape from the trap. I'll lose some atoms, which isn't good because as the density goes down, the Einstein temperature is getting even lower. And so I'm paying a price by losing atoms. But it's a net gain because I'm much more likely to lose hot atoms than cold ones. They have an easier time escaping from the trap. Okay? So now I have to choose the right schedule for lowering the height of the trap as a function of time so that I optimize the Einstein temperature of what's left relative to the temperature of the remaining gas. And so there's a evaporative cooling game on the Cornell-Wyman website you can play to get the feel for how you have to lower the trap height as a function of time in order to achieve condensation. But if you do it right, you can cool to a microkelvin or even better. But like I said, you lose some atoms. In the original experiments, I guess you can do a little bit better now. When the condensate formed, the number of atoms in the condensate was 10 million or so, about 10 to the 7. Okay? So a lot of atoms, with a sizable fraction of them in the lowest orbital, in a Bose-Einstein condensate. So we can try to understand why it occurs at about a microkelvin, given how many atoms are in the trap and all that. But actually, if we want to do that right, we have to rethink our theory a little bit. Because these atoms aren't really in a box. So in a box, there's no potential energy in the interior of the box, and then there are hard walls that the atoms bounce off of. But that's not what we have here. What we really have is a harmonic well, or can be well approximated by a harmonic well. So this is actually a picture of the potential as a function of position. In three-dimensional space, the potential energy depends on position, with the lowest potential energy being at the center, and then higher and higher potential energy as you move away from the center. Okay? So we'd like to understand the conditions under which, if we have a harmonic well, a finite fraction of all the atoms will be in the ground orbital of the harmonic well. Okay, and that's how we'll determine the Einstein temperature in the situation that's relevant to the experiment. Okay, so we have a three-dimensional harmonic oscillator. The trap might not necessarily be isotropic, but let's suppose it is. So the Hamiltonian is 1 over twice the mass of the atom, p squared, plus a potential energy, which is 1/2 m omega naught squared, where omega naught is the frequency of the oscillations in the trap, x squared plus y squared plus z squared. In other words, distance squared from the center. So actually, you can see the Hamiltonian splits up into a sum of three terms, which are all have the same frequency and are all harmonic oscillators, governing the x, y, and z position. So the wave function that is an eigenstate of the Hamiltonian can be factored into a product of three wave functions. An x-dependent wave function, which is an eigenstate of 1 over 2 m px squared plus 1/2 m omega naught squared x squared, an eigenstate of hy, an eigenstate of hc. And the eigenstate of the oscillator governing the motion in the x, y, or z direction is determined by an integer, which tells me how excited the oscillator is relative to its ground state. And there's a ground state, and then there are equally spaced excited states for the motion in the x, y, and z direction. And so I can specify the eigenstate by giving values of nx, ny, and nz, which can be 0 for the ground state, 1 for the first excited, etc. And we can define the ground state orbital's energy to be 0, so we don't have to worry about the plus 1/2 in the ground state energy. And the energy of the eigenstate is just h bar omega naught times the sum of the degree of excitation in the x, y, and z directions. Okay? So now, if we do have a condensate, arguing as before, we have a huge number of particles in the ground orbital. And so the chemical potential will have to be essentially 0, the activity essentially 1. And so, for the total number of particles in the excited orbitals, I sum over all the excited orbitals, and then have a distribution function for each orbital, which is e to the h bar omega naught, nx plus ny plus nz, in other words, the energy of that orbital, divided by the temperature minus 1. That's the Bose-Einstein distribution for this energy spectrum. Okay? Now, if the frequency of the trap, if it's a very soft trap compared to the temperature, then the sum over n can be well approximated by an integral. So if h bar omega naught over tau is small compared to 1, then when I increment at an x, ny, or nz, the argument of the exponential changes just a little bit. I can think of this as the Riemann approximation to an integral. So in other words, I can think of the sum as an integral over dimensionless variables x equals h bar omega naught over tau nx, y equals h bar omega naught over tau ny, and z equals h bar omega naught over tau nz. And so when I replace the sum by an integral dx dy dz, I get 3 powers of tau over h bar omega. So I'm writing down again the number of atoms in excited orbitals. It's tau over h bar omega naught cubed, an integral dx dy dz, 1 over e to the x plus y plus z minus 1. So this is just some dimensionless integral. Call it I. And the onset of Bose-Einstein condensation occurs when this formula, which applies when we have a Bose-Einstein condensate, when the chemical potential is essentially 0, we have some finite fraction in the ground state. When the number in the excited state is equal to the total number of particles, that's the onset of Bose-Einstein condensation. The Einstein temperature is determined by the condition that the number of particles in excited orbitals at temperature tau e is equal to the total number of particles. And E then is I, this integral, tau Einstein over h bar omega naught cubed. So this looks a little different than the formula that we had before. Because it's in effect a different type of dispersion relation relating the integer n to the energy of the eigenstate than for non-relativistic bosons obeying E equals p squared over 2m. Our formula, I guess I had a board here, didn't I? For the Einstein temperature, taking cubed roots, becomes this number I to the minus 1/3, h bar omega naught, and then n to the 1/3. And this number, evaluating the integral numerically, is 0.94. So that, for the case of a harmonic well, tells us the Einstein temperature. It looks rather different from what we found earlier, which was tau Einstein equals 2 pi h bar squared over m, number divided by 2.61 volume to the 2/3. But in fact, it has a rather similar interpretation, as we can, in both cases, think of the onset of Bose-Einstein condensation occurring when the typical interparticle spacing is comparable to the thermal wavelength. Now, let me convince you of that. So when the Bose-Einstein, so we imagine we're cooling down, the condensate is just starting to form. At that point, the gas occupies a volume in the harmonic well with radius r, and just trying to estimate things in order of magnitude, we know the potential energy for the typical gas molecule in the well at where the typical distance of the molecule from the center of the trap is r, is about 1/2 m omega naught squared r squared, and that'll be comparable to the temperature. The thermally excited atoms have this typical value of the potential energy comparable to the temperature. So that thermal radius of the gas in the well, not worrying about factors of 2 and stuff like that, will go like temperature over m omega naught squared to the 1/2. The interatomic spacing is the number of particles per volume to the minus 1/3. Call that A. I already called it A. So I can write that using this expression for the volume. Wait a minute, that's not the volume. That's the potential energy. Hold on. I see. For the volume, I'll just use r cubed. So for volume going like r cubed, A goes like tau over m omega naught squared to the 1/2 times n to the minus 1/3. Oh, I see. I'm sorry. Right. So this is essentially R, in other words, because that came from 1 over the volume to the minus 1/3. Right. And then, but I have to also keep track of the factor of n. So n to the minus 1/3, since we're talking about the number per volume. Now this is our thermal. Okay. Now we have a relationship between the Einstein temperature and n. It's here. I won't worry about the 0.94. But the number of particles, if I express it in terms of the Einstein temperature, is h bar omega naught divided by tau Einstein. So that means I can write this inner particle spacing in terms of the temperature as that's not right. Right, because it wasn't n, it was n to the minus 1/3. N to the 1/3, n to the minus 1/3, there we go. N to the minus 1/3 goes like h bar omega naught over tau Einstein. Just putting n to the minus 1/3 over here, and dividing by tau Einstein. So, I multiply this times this, and I get h bar over the square root of m, tau to the 1/2 over tau Einstein, or h bar squared over m tau to the 1/2 times tau over tau Einstein. Okay. So this is essentially the thermal wavelength. So in other words, when the temperature is comparable to the kinetic energy when the wave number is 2 pi over lambda, then this is the way lambda is related to h bar squared over m tau. So when the temperature is large compared to the Einstein temperature, the interparticle spacing is large compared to the thermal wavelength, and then when tau becomes comparable to tau e, then A is about the thermal wavelength. Okay? So, as we found in the case of the ideal gas in the box, onset of BEC occurs at interparticle spacing comparable to thermal wavelength. Right. So how do we know it occurs? We're cooling down, we have this gas, we reach this critical temperature, something spectacular must happen. What do you think happens? You're watching the gas, it cools, it becomes a Bose-Einstein condensate. You see anything? Yes, you do. So if you could continuously image the gas, you're cooling it down, it's just this big diffuse ball of stuff. You cool down below the Einstein temperature, and you see this little tiny cherry pit form in the center of the gas, where the density is very high. Why?
Because they're all in the ground state?
Yeah, because what you're looking at here is the ground state orbital with a huge number of particles in it. And the ground state orbital has a size which is small compared to the volume that the gas occupies. So it looks like a little nugget right in the center. So let's see, what is that ratio of R, the size of the ball of gas, to, I'll call it delta X, equals width of ground orbital Well, you learned this in Physics 12b, that the spread of the Gaussian wave function for a harmonic oscillator ground state is the square root of h bar over m omega naught. That sound familiar? You can look it up in your Physics 12b class notes. And so if I compare that to the thermal radius that we just estimated, then delta x for the ground state divided by R thermal goes like h bar over m omega naught times m omega naught squared divided by the temperature. Sorry, the whole thing to the 1/2. This is delta x, and this is 1 over m thermal, or 1 over R thermal, because this was R thermal over here. So that's h bar omega naught divided by the temperature to the 1/2. And when the temperature is the Einstein temperature, which goes like h bar omega naught times n to the 1/3, that'll go like 1 over the square root of n to the 1/3, or n to the minus 1/6. So if n is really large, when the onset of condensation occurs, the ground state orbital is very small compared to the radius of the region filled by the gas. And we see many particles right in the center, sitting in that ground orbital. So this is when tau is comparable to tau Einstein. And that's what they see. So in the original experiments, like I said, the number of atoms was about 10 to the 7. And the total volume occupied was, well, it doesn't matter. Anyway, this was smaller than the thermal size by a factor which was more than 10. So it looked like a little nugget in the middle.
Could they see it?
Yeah, so the way you actually see it, and there are pictures of it happening, animations of it happening in this Wieman Cornell website, is one good way of imaging it is, you see, you don't want to, if you take a picture, you can, there are several ways of doing that. You can blast it with laser light, and that badly disrupts the condensate, but that's okay. You do the experiment many times, and at a certain estimated value of the temperature, you take that snapshot, and you can get a picture that allows you to find the density profile. And you see a picture like that. Another thing you can do is you can turn off the trap. Suddenly the harmonic well is gone. There's nothing holding the atoms in the bottom of the well. They still have some kinetic energy, either because there's some momentum distribution in the ground state orbital, in the case of the condensate, or thermal energy for the rest of the gas, and so it starts to spread out. And you can measure how rapidly it spreads out as a function of time and get a momentum distribution for the atoms at the time you took off the trap, and then from that momentum distribution reconstruct the position distribution when you turned it off. And you can see the picture that way. In his article that I linked to the website, Ketterle also described something else, which was an early experiment they did where they built two condensates. So you essentially have lots of atoms in the ground state in each of two traps, and then you turn off the traps and let them go so they fall. But the traps, as they expand, also collide. And then you can measure the distribution of atoms as a function of position, say in this plane. And what do you think he sees? Well, suppose you were doing the same thing with light. Suppose you had two sources of coherent light, two lasers, coming from different directions, and shine them on a screen. What would you expect to see? there'd be an interference pattern. Physics 12a, guys. And so you would see fringes. And what they said saw the first time they did this experiment were fringes in the atomic density. Because the two condensates are interfering with one another. What determines the spacing between the fringes? Well, there's some de Broglie wavelength for the atoms, some de Broglie wavelength difference between the two condensates, so you can estimate that you should, under the conditions of their experiment, see fringes which are separated by about 15 microns, and that's what they see. So this is quantum interference between atoms, but it's not like physics 12b when you talk about electrons going one at a time through a pair of slits, giving rise to an interference pattern. In that case, you send a single electron a huge number of times, and you measure the position behind the two slits each time, and over time you build up an interference pattern. But this is real-time interference between atoms, much like the real-time interference between classical electromagnetic waves. So it's the atom analog of a laser, an atom laser. Now, since that article was written by Ketterle in '97, the techniques for cooling atoms and making BECs have been used in many applications. And one of the things that has become a very active area is trying to study the effects of interactions among particles. And the ability to make a Bose-Einstein condensate is sort of the standard tool that's used in all these experiments. Now, there must be hundreds of labs that can readily make Bose-Einstein condensates. It's become very routine. And one of the things you can do with them is you can consider making a kind of synthetic material with an optical lattice. Well, an optical lattice is just an interference pattern set up between lasers, let's say two counter-propagating lasers. They make a standing wave, and you can control the intensity of the light and therefore the height of the amplitude in the oscillations of the electric field in the standing wave. And if you turn on such an optical potential or optical lattice, starting with the Bose-Einstein condensate, turn it on slowly, this evolves to a kind of crystal which has, if you do things right, 1 atom per potential minimum. It's like a kind of synthetic crystal. And unlike normal solid-state materials where you're kind of stuck with the parameters appropriate for the type of atom in the crystal, in this case we have the freedom to change the strength of the interactions between the atoms. They, in principle, can interact by tunneling through the potential wells. I mean, they see a potential because there's some differential stark shift. They have an energy that depends on the electric field, and because the electric field has nodes and antinodes, their energy depends on their position. And an atom can tunnel through at some rate which depends on the width and the height of this potential. As we change the height, the tunneling rate changes. And so we can vary the rate at which they tunnel and study phase transitions that occur that depend on the relative strength of the on-site interactions when two atoms are sitting at the same site in the lattice and the strength of the tunneling from site to site. So what happens is, for a given strength of the on-site interaction between atoms, is that there's a kind of phase transition that occurs as we vary the height of the potential. When the potential is very high, then the quantum ground state of this synthetic material is one where there's essentially 1 atom per site and no flow of atoms through the lattice, it behaves like an insulator as far as conductance of atomic current through the lattice is concerned. But if we lower the height of the potential enough, then there's coherent tunneling from site to site, and it behaves like a conductor, or really like a superfluid, despite the presence of the lattice. Well, the transition between the two is called the Mott transition. It had been predicted by theorists years ago, but had never been seen in any material until it was studied using optical lattices filled with Bose-Einstein condensates. And that was done about 10 years ago, and since then there have been many experiments synthesizing different types of quantum many-body physics using optical lattices filled with Bose condensates. Okay, so next time we're going to start turning away momentarily from the quantum world and talk about good old 19th century thermodynamics for a while.